welcome to next. Today we're going to be doing 1996 CAP Part B's question 1. So this question is about gravity. So we see the study of acceleration due to gravity of the Earth can be very interesting. Variety of factors such as the Earth's spin and altitude can result in variations of g. In this question, we shall investigate these variations. So we want to find expression for g at the Earth's surface, right? So we know that force Fg is just equal to g, big G, mass of the Earth, mass of whatever object over r squared. And this is also equal to mg, right? You want to find this thing. So we just cancel out the m's. You know, this is the radius of the Earth, so we get g is just equal to gm over radius of the Earth squared. That's part A. Simple. So I want to modify our expression to give the acceleration due to gravity at an altitude of h above the Earth's surface. And we can see that h is much smaller than re, so we can use this simplification formula. So we can just say g is going to be big G, m, or just g prime. Radius of Earth, I'll just write r in this case, plus h squared. Right? So we can simplify this. We can use this simplification approximation method. So we just first take out a factor of r squared from the denominator, so we get gm over r squared. So the inside will just be 1 plus h over r squared. Now we can see gm over r squared is just g, original g. So we just call it g naught. Now this can be expressed as 1 plus h over r to negative 2. You can apply the approximation for small h's. So it's basically this 1 plus something like alpha over n is just equal to 1 plus n alpha. So here n is negative 2, right? And alpha is h over r. So this equals to g naught times 1 minus 2h over r. Right? So now we calculate the weight of the man at the sea level. So this is just mg. So weight is just equal to mg. Plug out int, we get about 88.2. Plug that in, we get about 882.9 newtons. And we can plug this in as well. So weight on top of Mount Everest is just going to be mass still times g naught, same as this one, times 1 minus 2h over r, where h is 8,000 meters. So this value will give you 880.7 newtons. So we want to calculate the percentage difference, right? So let's calculate it. So it's just going to be 882.9 minus 880.7 over 880.7 times 100%. This gives you, like, they're different by about 0.25%. And this is the answer done. Now for part C. The acceleration due to gravity depends on the latitude because the Earth is spinning. Find the percentage difference between g at the poles and at the equator due to Earth's spin. So I want to consider weight, right? So, you know, g at the equator is just g, gm over r squared. That's g naught, right? And let's draw Earth. Consider this is at the poles, no spin. Consider at the equator, right? It's going, you're on the surface and the Earth is spinning, so you're going circular motion, uniform circular motion. So it's going to be, have to be a force pointing this direction. And also, if you're standing there, there's going to be gravity pointing this direction as well. And then there's going to be normal force canceling out. So these should all be 0. So Fc is part of gravity. It uses gravity for Fc. So your normal force usually is equal to Fg, right? Just like in this, on the poles, it's this. But on equator, it's going to be N is equal to Fg minus Fc. And we know the force of gravity is just G, big M, small m over radius of the Earth squared. And Fc can be written as m omega squared r, right? So this is minus m omega squared r. Now we know normal force also has a factor of m in it, so we can just cancel out m here, and m here, and you get g, right? This is g prime. So your g prime is going to be, see, g big M over r squared is exactly g naught, so equal to g naught minus omega squared r. Now we know omega squared is just angular frequency, right? So it's just 2 pi, angular velocity. So it's just 2 pi over the time it takes to complete one cycle, which is 1 day. So it's 24 hours times 36,000 seconds. So you plug that in, we get g prime is approximately 9.776 meters per second squared. So I want to find the percentage difference, right? So we get our original value, so 9.81 minus 9.776 over 9.776 times 100%. This will yield around 0.348% difference between the gravity at the equator and at the pole. So C is done. Okay, so for part D, you want to find an expression for the magnitude of the free fall acceleration of an object near the surface of the Earth as a function of the latitude theta. Assume the Earth is spherical and spinning, right? So first, you know the centrifugal acceleration, right? Just going to be equal to omega squared times r. But then this r is going to be this r, not this r. We know this theta, right? So we can use this as theta as well. So project it up here, we know this r is just equal to the radius of the Earth times cosine theta. So this is going to be equal to omega squared times r cosine theta, right? So you can draw the surface of the Earth at whatever you want. So like this is theta. So here we have gravity going this way, right? Center of acceleration going this way, right? So then there will be equal outwards. So we add these two vectors, we get that the free fall points in this direction, right? And we know that this is shifted outwards like this, right? This is theta as well due to opposite angle, so we can use cosine law here. So you get your free fall acceleration, I'll just call this a squared, is equal to your g squared plus your centrifugal acceleration minus your g minus your centrifugal acceleration times a factor of cosine theta. Right, there's a 2 in front as well. So what you want to do, you just find a is equal to the square root of this thing, g squared plus ac squared minus 2g ac cosine theta. That's done. So I shall do a bit extra. So you want to find, if you want to find the part perpendicular, right? So you can do like this. Say you have a Earth like this, and this is a theta. So here your radius here is be r, right? But this radius is just going to be r times cosine theta. That makes sense, right? So your centrifugal acceleration is just going to be omega squared r cosine theta. Say you want to project it back into this direction, the perpendicular to the surface. You'll get in this direction it's just be omega squared r cosine squared theta, because you're doing cosine theta again, because this is theta as well, right? Due to opposite angle. So your acceleration perpendicular to the Earth's surface is going to be g prime is equal to your g at this direction, right? But g at this place is different because it's just g then minus omega squared r cosine theta squared. This is a bonus, bruh.